Hello, and thank you for joining me for this presentation of single case research design. To start, I'd like to do a bit of review. First, let's take a look at Inter-Observer Agreement. Remember, this is our reliability of measurement data. Here we have an example of data on Jane Doe talking out without raising a hand and being called on first. So each time the behavior occurs, it is tallied. Here are 7 pieces of data. On the 1st and the 6th day, a second observer collects the same data. Take a second and make a comparison here. We have 7 and 6. What's the reliability here? 6 divided by 7. On this day we have 7, and again with 7 agreement. What's the reliability here? 7 divided by 7. Each time we take that number and multiply it by 100 and we will get the percent agreement. The average is 93%. Is that what you calculated? That's acceptable inter-observer agreement. By establishing this kind of agreement, we know and can trust that the data are accurately recorded. Now, in the case of interval recording of data, rather than the frequency data we were seeing previously, we have to look at each interval to look for agreement. We have 1 agreement, 2, 3, 4, 5, 6, 7, 8 agreements out of 12. How do you calculate that inter-observer agreement? 8 agreements over 12 intervals, which is 67% agreement. Is that what you calculated? Is that acceptable inter-observer agreement? Now, I want to review or talk about some variations of the multiple baseline design. Remember, in the previous module, we learned about the multiple baseline probe design, and there are 2 predictions that must be made prior to beginning this design and expecting to see 2 predictions must be made if you expect to establish experimental control. First, the behaviors, conditions, or participants must be functionally independent, meaning those will not change or be highly variable until intervention has been applied. But at the same time, they must be functionally similar, meaning they will each respond once the intervention is applied. Let's look at the different designs. This is a multiple baseline across participants. This one is across settings or conditions. As you can see, it's the same behavior, just different classrooms. And this one is the same student, same classroom, different behaviors, different skills for each tier. Notice this has intermittent baseline data collection. That's why it is a multiple probe across settings. You may have to have a brief withdrawal to show that experimental control. If you ever read an article that uses a delayed multiple baseline, that means each tier was not. That means the data across each tier was not collected simultaneously. So it is a weaker design. And also, if you have a rigid time criterion to introduce an independent variable, that's weak. It needs to be only after the previous tier meets a preset criterion would you start intervention in this tiers below. In terms of testing as a threat to internal validity, it's possible because generally The multiple baseline or multiple probe design is used on academic skills because they aren't reversible behaviors. So it's possible testing could be a potential threat, meaning students will learn the answers through a facilitative effect, or they may be tired of repeated testing and it will have an inhibitive effect. But to control this, we want to decrease any procedural contrast between conditions, shorten the length of the sessions. We only want to reinforce alternative behaviors and not being correct or incorrect. And history training would mean they're exposed to the materials, formats, trainers, and procedures prior to beginning the study. The multiple baseline or multiple probe design is useful with group data. You could use an intervention for a classroom. You can plot that group data, and if the group meets a criterion by a mean or average, you can begin the next tier. You want to plot or table individual data to permit independent analysis for each student. Now, why are some hesitant to use multiple baseline or multiple probe designs? Well, it requires a significant amount of resources to collect data across several participants' behaviors or conditions. And for some of those tiers, a prolonged baseline condition can create a negative experience for participants. Delaying the implementation of intervention may at times put the participant at risk. Now for a new design. Changing criterion design. This is when we have stepwise changes in performance criterions and we target behavior as evidence as a functional relation. If you think about it, if you were going to set a goal to run a marathon, would you just expect that the next day you would run a marathon? Some behaviors are not possible to immediately meet the ultimate criterion. So when you need stepwise changes to build an endurance, we may need stepwise changes in performance. We will set a pre-established criterion, and when the student meets it, we bump it up to a higher criterion, and we do that in stepwise changes, and that really creates a number of overlapping A/B designs. This is not appropriate for evaluating acquisition of a new behavior, because behavior must be already in the student's repertoire. It's really for shaping programs. We're shaping behavior. We would like to build fluency objectives, or perhaps the student is on a DRL or a DRH schedule. If you're unfamiliar with your differential reinforcement interventions, look those up to see in reference to this. The guidelines for changing criterion design is that you have to have at least 4 or more changes. The size of the criterion change is rather arbitrary. It varies in size, but basically you just want it to be large enough to jump above data variability. The general rule is 15% above preceding criterion performance level. The number of days at each criterion would be a minimum of 3 or until stable data, and it can vary across the criterion. Criterion design is to have a return to a previous condition, so in essence you have an AB design built into it. You establish experimental control when you have immediate and abrupt level changes at each criterion with 0% overlap. You want to combine this with a multiple baseline design, return to a previous criterion level, return to the baseline. These are all ways to increase that experimental control. But don't be caught in a common error of limiting the opportunities at each criterion level just to ensure that it looks like a stepwise change. They must always be able to meet the target number. Now let's look at some comparative intervention designs. Why do we have to consider this? Well, we have a couple of really special threats to our experimental control when we have comparison designs, when we're comparing 2 different interventions. See, if you look at this example, here's your baseline data, and here's how intervention B works. And here's baseline data, and here's how intervention C works. As you can see, intervention B shows an increase in trend upon intervention, whereas intervention C shows no change. Take a look here. If you have baseline data, and then you see that increased, that accelerating trend in the B condition, and then in the C condition, we continue to see that trend. One might say, C, intervention C works, but we know it doesn't. You may also see this. Increase with B, but with C, it decreases. And some say B may really worsen the behavior, but we know that it's not true. Why might this happen? Well, there could be a sequence confounding. Could be a carryover effect. Either this first changes the response to this, or this data is just a continuation of having this happen first. So let's look at some designs. Multiple treatment design is an extension of an AB-AB design where the baseline is still very important for extending the external validity. Interventions will result in more efficient learning or rapid deceleration of challenging behavior. Some examples might be, which of 2 ways to design my classroom increases on-task behavior or on-schedule behavior? Or you might say, which increases compliance? Student choice activity versus teacher choice activity. See, in both of these cases, a baseline condition would be difficult. So a comparison design of a BC-BC would be another alternative. Here's the example. So this might be intervals on task, and here we have baseline data, and then we have 2 new classroom arrangements to test, which might help students be more on task. However, that's subject to that sequence effect or that carryover effect, meaning if intervention B is followed by intervention C, there is a sequence effect that only because it goes in that order is there a change. Or the carryover effect, that means intervention B impacts intervention C. So we need to counterbalance across students. So the second student might have an intervention A, CB, CB to look for different effects. Another alternative to a comparison design might be alternating treatments design. This is the rapid alternating application of 2 interventions to compare the effects on behavior. So because we're alternating a rotation of interventions and they're randomly implemented, we can try to decrease the threats to the carryover and sequence effect. But what we're ultimately looking for after we compare the level trend and stability of each treatment path is which produces more change, which produces more rapid change, which has more stable levels of performance, and which has the most data points falling outside the range of other interventions in a therapeutic direction. Here's a picture. In this case, we have a baseline, and then we have 2 different interventions being compared. You see, these could be daily sessions. That couple days we had this intervention, and then a different intervention, and then different intervention, and then they're connected to see, well, intervention triangle is obviously more efficient and more effective. You don't have to have a baseline condition for an alternating treatments design. You can go straight into your comparison phase and then remove and only implement the best condition alone to show that there is no sequence or carryover effect. Having both would be ideal, or perhaps the advantages to an alternating treatments design is that it does not require treatment withdrawal. It minimizes those sequence effects. It can be used with unstable data, and the intervention can begin immediately. So these are all very appealing advantages. Only problem is, what if you cannot use 2 different interventions on the same behavior because they are not reversible behaviors? In that case, we do an adapted alternating treatments design. That's when we compare the effects of 2 or more interventions on 2 behaviors. For an adapted alternating treatment design, we take 2 or more behaviors or sets of behaviors that are similar but functionally independent. Independent variables are applied to these separate behaviors that are of equal difficulty. For example, here are 2 interventions, a system of least prompts and constant time delay. We can compare these 2 interventions for efficiency and effectiveness across 2 very similar behaviors. One, packing a suitcase, and the other, packing groceries. So the alternating treatment design does not require the behaviors to be reversible, but the equal difficulty of behaviors is critical. Let's take a look. Here is two different sets of behaviors. So there are two different sets of sight words being evaluated against two different interventions. This one is a picture alone. So these sight words are learned with a picture. And this one is picture and text. So this is presented with a picture with the text underneath of it. So we can compare which intervention allowed the student to learn more effectively and efficiently. And as you can see in the PTM with the picture and the text, the sight words were learned faster or at a higher level. So your independent variables in an alternating treatments design, essentially the order of implementing the independent variable has to be counterbalanced across the time of day, teachers, and settings. So they're alternating across all of these different scenarios. Usually it's a morning and an afternoon session so that they can be counterbalanced across days. And then in the final phase, use the most effective independent variable alone. And this will help you rule out any sequence effects. Just important to remember that the participants have to be able to tell the two different independent variables apart. They need to know which independent variable, which intervention they're receiving at any given time. You also have to report your reliability and fidelity measures for both interventions. And it's possible adding a control set of behavior that is not treated or does not have an intervention to improve that functional relation and experimental control. So these multi-treatment designs can be impacted by sequence and carryover effects. By counterbalancing, we can rule those out as threats to your internal validity. But remember, those two intervention conditions must be discriminable by the student. Alternating treatment designs have that sequence effect controlled by rapid alternation of the interventions, whereas the carryover effect is likely to be detected using a baseline or a superior treatment alone condition. The adapted alternating treatment design also has sequence effects controlled by that rapid alternation of the interventions. And again, the carryover effect can be detected by applying the intervention to separate behaviors, but even more so by having a third set of a control. Here's a summary of the comparative designs and when to use them. Thank you for your time and attention.